So, last week we started to discuss about the mini project. So perhaps today we can talk about more detail about each of the mini project so that understand what my requirement is, and then you can start to look into that. So we have a number of the mini project here. The first one including a simple winding of the PM DC motor. So this is a hardware project. I think you did that in the past about. Have you ever done a construction of a simple motor? Maybe just a few winding of motor. I think first of all, I can show you this YouTube video. Probably you can able to search up for some YouTube video. I think there may be some. So here will be, let me see again. So you can see that that can be quite simple and straightforward, which you can see that a simple winding like that, putting a simple battery and become a motor. Have you seen that? Yeah, I think many of you may have seen that. So this project quite simple and straightforward. Of course, you need to see how you're going to construct this simple motor. But more importantly, will be find out why you can do that. For instance, where is the PM look like? Which one is PM? Of course, the bottom one is the PM. And then what is the winding, single winding? You can make it a DC motor. How we increase the speed and how to make it more stable. And for instance, what other variation you can do? Can you sketch the magnetic flux? We learned the magnetic flux, but how does the magnetic flux look like in here? What other variation for this kind of the single winding transformer? If you go to the website, you can see, you can search for many different type of this simple motor. So you firstly in your project, you already explain why this motor work. Usually you can see that we have a current here. We have current pass through the winding. So this current need to interact with the magnetic field so they can produce the force. And then you can see that we have PM in here in the bottom. How does the PM usually go through the middle? But now it seems you can interact with the copper wire. So why is that? How is that? So that's the thing you need to examine. Ask yourself, can you sketch, examine, prove the magnetic flux in which direction? If you want to increase the force, increase the speed, what you can do? And another extension would be you can also make that in the YouTube video, you can see many of them can become a vehicle, can move around like a magnetic train. You can move around a magnetic coil winding. I can show you more videos. So just a simple topic like this, you can able to create your own mini project, examine about where's the magnetic diagram look like, how we improve the performance, how we control the speed, what kind of force you can able to produce. You see a really DC motor. In normal DC motor, we have commutator and carbon brush, but this one doesn't. So how this work? So that's a quite simple project, but have a lot of the research content. You can see that today, you can from YouTube video, you can see many new items, special item, and then how you can observe this kind of phenomenon. Okay, any question? Simple project, but not quite special, right? So that means the deliverable will be, you need to show me these prototypes. Of course, you can show me these simplified prototypes, but if you're able to modify it to make it more good looking, stable, high speed, more winding, then it will better. This is only vertically rotation. Can you change them in the horizontal, like vehicle moving on the road and like that? So go to many of the YouTube videos, you should able to see many examples. This show you a simple winding PM motor. So the deliverable including report detail the design, how to design them. To design such a motor, you need to see what is the torque speed you want to design, what kind of winding you need, and also the theoretical principle like the magnetic flux analysis, how the magnetic flux look like, how you interact with your winding, current carrying winding, how to optimize the performance. So this is not a complicated project, very simple. Even though some of the high school students have done that in the past, as some of their souvenir project, but as a university student, postgrad student, we need to see the theory behind how we improve it further, how we examine about the phenomenon. Would there be further work on this one? Further work, like if you're given the project, can you improve, become a more fantastic motor? So that's the thing you like to do, okay? So this component is very simple, straightforward, because you just need some copper winding, copper wire, a battery you can get from anywhere, and also a PM available everywhere. You can get it from Amazon or wherever. If you like, I can also order some for you. Then you can start to make your own construction. All right, any questions? So next one is to how to control inverter output using a microprocessor. I think all of you may have some experience how to work with a microprocessor, even though like Arduino, Raspberry Pi, and STM. Yeah, there's a few examples. Then you can see how you start to use them to program with a inverter. You see a PWM inverter, usually we have got the pulse modulation waveform. We can use it to control the pulse modulation to make it look like a sine wave. A sine wave usually this kind of waveform, but we can use PWM so that it make it look like changing the pulse wave in order to make it emulate with the amplitude. So that's how we look into that. So you can use any one of the design tools to do that. And then what you need to do is to make up your PWM generation using microprocessor, and then to show me how you're able to obtain waveform. For example, in a deliverable, then you can show us about your hardware, how you can produce the waveform. So that means in your deliverable, it will be your microprocessor source code and report containing your oscilloscope waveform and capture some of the waveform, how you're able to represent a sine wave. Are you able to use it to represent different kind of the voltage, frequency, and sine wave? Probably you can try that. Maybe you can some 60 Hertz, we can reduce to 30 Hertz, or we can change the voltage, change the frequencies. That is the basic requirement, how we can look into that. So next project is the MATLAB. So we all know MATLAB and Simulink, or even though you can use Python to look into that. So in the MATLAB environment or Simulink environment, you do have a machine environment, which you can able to include an industrial motor model or maybe inverter, and then develop your pulse modulation to control the motor. And for basic motor control, we have to use something called the constant V over F control. I'm not quite sure you heard about this VF control. So this control is to change the voltage and frequency simultaneously so that we can able to vary them both in a same manner. In this case, you can make sure the magnetic flux to go to the motor will be the same. So that's how we look into that. So by doing this one, we are able to optimize the motor performance. It's a maximum performance. So this is only a software environment. You don't need to produce any hardware. You just use MATLAB to produce the real control, how to control the motor, maybe as a closed loop control to the motor. That may including you may use produce your simulation model of your MATLAB, or maybe even though you can do everything by Python, and then to develop all your model, show me the model, and then do the complete simulation, including the torque, speed, and also current waveform under a few test conditions. For instance, the torque equal 10 Newton meter, 20, 30 Newton meter, the speed will be changed from 0 speed to ramp up to 60 Hertz. So a few testing conditions that will do. You don't need to give many conditions. Just show a few of them to show you fully understand how to use that. All right? The next thing to do is EMI. You see in electromagnetic machine, EMI is an important topic. EMI is the important component to provide the magnetic flux. But magnetic flux inside a motor can also have leakage. So this leakage may spread across to other locations that may affect the survival or the safety of other electronics. So for instance, if you have DC motor, you can see that once you turn on this motor, by the side of some of the machine, maybe your phone or maybe your TV, you can see some disturbance. So that common thing, you can see that because once you turn on the motor, you can see some leakage magnetic flux will be in the environment. And also the motor inverter system, because you need to control the pulse rate moderation. The pulse moderation, all these amplitude and duty are really subtle. So if you don't control them properly, we end up with a kind of the nonlinear. So that means we cannot control the waveform properly. So that means to study the EMI was also important. So in here, it's only a software project or desktop development, no hardware. So you have to develop the standard, how to look into the standard, how the standard are related to the commercial product. For instance, you can check a few commercial motor or inverter to see do they have a EMI requirement. What are their requirements? For example, this motor need to meet the IEC standard 61,000. So why is that? What kind of the harmonic will be their limitation? So you can give some analysis to see how they look like. So this don't have any strict answer, but like you to understand more about the EMI standard. Because all the electromagnetic, like the motor, inverter, they highly relate to the EMI environment. Because the genuine EMI, they also scare about the EMI. For all the product, they need to have some immunity to the EMI so that they can survive under certain EMI condition. So that's how this project like you to do. So next project is the dynamometer. Dynamometer, anybody can tell me what's meaning of dynamometer? Mm-hmm. Mm. I'm going to install a dynamometer in my lab, in my EV lab downstairs, right? My BSP lab. So anyway, when we have a voltage source, if you want to test the output power for power supply or voltage source, we use a resistor to test it, to test the voltage and current, test the power. We can vary the resistor, we can vary the current to see how the power look like. A motor, how do we test a motor? We connect a kind of the so-called dynamometer to the motor shaft. So that means we use dynamometer to emulate about the resistance. Like we can control the loading torque, loading resistance in order to measure the speed and then adjust the motor current. So that is dynamometer. With the dynamometer, we're able to test the motor properly. So that means we have a motor here. We connect dynamometer to the shaft. So once we drive the motor, we don't drive without dynamometer. You may drive the motor in open loop, so-called the open circuit test. So because that without any loading, motor current have carry little or negligible current because it have no loading. So by using dynamometer, we can increase the friction for the shaft, just like when you test a vehicle. If you test a vehicle with open loop, that means you lift up the vehicle, let the wheel to freely rotate. You don't have any load. So what we need to do when in my BSP 630 lab, I'll put the vehicle into a dynamometer, like a running machine, a roller machine. And the roller machine creates the friction. Then when I drive the vehicle on the roller, then the vehicle don't need to go a long path, just stay in the inside lab. Then we can able to drive the vehicle under the various road condition testing. So that's the thing we tend to use. Okay. So that means in here, we're not asking you to build up an EV dynamometer, but just to see if I attach a motor to a dynamometer, to a small dynamometer, and then in this case, the dynamometer will be look like a DC motor, but working reverse manner. Reverse the DC motor become a generator. You see the motor here connect to a generator, then the DC motor power will transfer the generator. And then if generator output more current, connect to some resistor, you create more resistance. So that's to say you can use this kind of the generator or dynamometer to create a loading environment for the DC motor testing. You can adjust the DC motor load. So this project is ask you to connect a DC motor with a dynamometer, which is just another DC motor, to create set up a functional dynamometer test setup. So imagine you like to set up a DC motor testing system. DC motor connect to a generator. Except the generator, you can able to conduct a field test for the DC motor. That's what we mean. So that's to say, you need to produce a report to show how you design them, how do you calibrate them, how do you calibrate the torque and speed characteristic for the motor, and how you present the data, including you can have some torque speed curve and efficiency curve. So you don't need to examine with high detail, but I would like you to understand how to set up the dynamometer in case you are given a task to set up a dynamometer using a DC motor. How are you going to do that? Yeah, for instance, you can there's a many website equation we'll show to you because we know that in next few chapter we will learn the DC motor, then we will learn how we use the DC motor as a generator. How we'll examine about the output current for the DC motor. We can therefore see how we're able to test the motor under different scenario. Okay. So that means this one only need to show us how you make the design for the dynamometer and how to calibrate the testing to produce torque speed curve and how you're going to present the data in form of the efficiency and the torque characteristic. Very straightforward, yeah. So next project is a web programming for machine lecture. In my course here, I'm going to have 15 lectures, right? Each one of them will have different topic. So in here, I would like you to see if you're able to convert some of my lectures into a web-based lecture material. So for those students, they like or they have good experience for the web programming, how to program your website, you can see how to convert my lecture into just a web programming. But bear in mind, we are not just ask you to save the file into the HTML, so straightforward. I would like you to create more teaching or learning environment, including how to make the presentation become more effective, how to produce more interactive element into your teaching, how to able to provide something like voice synthesizer or some exercise, automatic exercising, this kind of the teaching environment, rather than just save the file in the HTML. That will be very low mark. If you just put my lecture notes, save them in HTML, put into the website, everybody can do it within 10 minutes, right? So you think about how to make it more interactive, how to enhance the learning. So you don't need to cover all my lecture notes, a few chapters to show them. into one of the website how that can be done. So there's many software nowadays you can make use of them. For example, the front end framework, back end code editor, many of them you can use some of them to assist your web programming. For that's mostly for those students they like the web programming. They've been doing some of their website. Then you can try that. All right. Any questions? Next is again is the hardware project. So this hardware project is to try to develop a 6-step inverter. You see, you're all my PhD student, you do need to have some hardware experience. So for instance, this one is 6-step inverter. You see, most of the PWM inverter to drive motor, usually the PWM are quite complicated. We got a lot of the different kind of PWM control strategy, like sinusoidal or the vector control or space vector, many of them. But one of them, the program is quite simple, called 6-step inverter. We convert the inverter into 6-step. Let me see if we're able to do that. For instance, you can create a 6-step like this. So here will be just a few steps. But if we look at it carefully, then you can see that we're able to create a more look like a sideway. Something like that. Of course, this is not really a sideway, but more close to sideway using really simple steps. Usually you can use PWM, you can use those PWM. I don't know how to solve the PWM. There's a very complicated PWM. We can also use them to emulate a sideway, right? But this PWM waveform, they are multiple. They got 20 kilohertz frequency. But this one only the same frequency as our sine wave. But using this 6-step inverter, we just program the inverter into a few steps to make it look like kind of the sine wave. Obviously, this one do a lot of the low order harmonic, which we don't quite like. But you can see that before we develop a microprocessor, probably 50 years ago, when we don't have the microprocessor, if you want to drive motor, then either turn on, turn off, we can use transistor to develop this 6-step inverter, which is able to make it more look like sine wave. Then we can able to use this method to control the duty ratio, control amplitude, control the frequency. That's still really good sine wave control to our motor. So that's how we did that in the past. So the 6-step inverter come in at that time is a history of time. We use this 6-step inverter to drive this motor. You can program them using your microelectronic to see if you're able to drive the waveform. You need to see how it's going to produce this waveform to control the motor at various speed and various amplitude. You can still using the constant VF control because in this thing, the frequency here will be this period. You just control off time to control the speed of the motor, and the amplitude will using the duty control to control that. So we can able to develop this kind of control mechanism to a microprocessor to do that. So this is quite a simple type of the 6-step inverter. It's really famous in the history of the motor development. Some of the simple systems are using this. Some of the simple inverter, when we produce the AC waveform, we can also use this. This waveform, after we pass through a low-pass filter, then that will become just a sine wave. So this is one of the methods I usually teach the student how they firstly understand the operation of an inverter. Have you learned this 6-step inverter in the past? No? Okay. You go to the website to see able to get some information, and then this is the typical waveform for 6-step inverter. Just a few steps, then you are able to create this funny shape. Let me. Another project is DC motor drive. We're going to learn the DC motor in 1 to 2 weeks' time. So DC motor is one of the simple motor. We can easily control DC motor using a DC voltage source. We are able to adjust the DC voltage. by using some electronic component to adjust the motor speed. And you can also use the PWM mechanism to control the motor. So in here, they need to develop the gate drive circuitry, the DC motor driving system. So this project is asked you to develop DC motor experiment by using a connection of DC motor and also inverter. So like in here, you can connect two DC motor together. One can be for motoring, the other one can be for generator. And then you can, one side, you can use a PWM to control one side of the motor. The other side of this motor will become just a load, because I don't want to just simply to drive this motor in open circuit without any load, because you can't connect a DC motor to a resistor. So you need to connect the other side using a DC motor as a load, just like what we did before for the dyno, for a dynamometer. But this one is not focusing on the dynamometer, but focusing on the how we drive the DC motor under low environment. The low environment, just like your DC motor in here, putting resistor, then you can use it to control. For instance, you can do it like this. For instance, if you have a motor in here, it's also DC motor. And then when you have sharp here, you can also connect another DC motor here. And the output side in here, then there's a sharp. And then with DC motor here, you can just connect a resistor. You adjust the resistance here, that can automatically become your dynamometer. So, and then in here, you just using your normal PWM to drive your DC motor. So that's as this kind of the setup, you can therefore examine how DC motor working. I'd like you to produce different kind of control algorithm for DC motor to see you are able to control the motor torque and motor speed under certain load conditions. The load will just simply represented by DC motor connect on the other side of the shaft as a load. So this one focus on the DC motor drive. For previous one, focus on the dyno, how to develop the dynamometer. So this is also a hardware project anyway.
So basically,
yes,
the resistance can be adjust, so we can have many levels torque to output.
That's why the amount of torque is decided by you, because we only do a mini project. We're not demanding for high power, wonderful torque control system.
Yes, I mean the other DC motor to use a dynamometer. He connect a resistor.
Oh,
so
right.
Maybe the resistor can be adjusted so we can output different level torque.
No. In this one, just now I write down using resistor to program the load. So that's simple way to develop. But for this project dynamometer, then we have to use more complicated way to do that, not only using simple resistor. In the lecture later on, I will say more detail how we program this motor into our generator. In this case, we may need to use a buck converter, maybe H-bridge, to connect to a DC motor as a dyno. We adjust the duty ratio or PWM for the dyno to do that. So this one expect to focus more on the dynamometer. The other one, you can just using simple resistor. But this one expect you to use H-bridge or half bridge to do that. So another one is also a desktop analysis. So in the market, there's so many different kind of the electrical machine types. So in here, we'll ask you to examine different type of the machine in the real world application, like electric vehicle, industrial pump system, drone, or many household appliance. They're using many different kind of the electrical machine. So you're going to compare them to see this one using this motor, the other one using induction motor, maybe synchronous resonance, some of them using PM motor, many different motor can be used. So you need to search from all the website to see, take a quite a few example, what kind of machine are they using, why they need to do that, which one is better than which one, which application to use which machine. So do some analysis. So you may need to look into how the machine torque and speed characteristics are related to the application. Because some of the machine really good torque performance, then we may need to look at better control for the motor, more high performance for the DC motor, or maybe induction motor. Some of them may also looking into the cost analysis. Some of them too expensive, we don't use that. Some of them are use PM motor, PM expensive, some applications don't use them. So that means in here you can examine about torque speed characteristic, efficiency map, the cost, reliability, and also the control. So you might also adjust their recommended choice. I mean, why this application you use this motor. You can search from the website to see this application to use this kind of motor. And then you can double check to see would there be any other alternative. Because the application maybe has done 5 years ago. Today, there will be other alternative, better way to do that. So you to take a few example. You don't need to take 20 or 10, so many. Just a 3 to 4 example. And then to show what you have done the analysis. Because for this desktop study, we're expecting the total number of the pages for the report only desktop maybe 12 pages or more. So you don't need to do that many analysis. But I like to see good analysis, how you can analyze the application. The thing is, most of our applications is not available. You only can download their datasheet to just have a name to see what motor do they use. And then you try to develop your own analysis. Why they to use this motor? What kind of torque, speed, or performance they like you to have. So that's the difference, right? So this kind of project is really much, don't have any fixed answer. All up to you how to analyze that. But I like to see how you analyze a motor system properly. So that's why this project, you do need to examine for at least more than 1 month to do the job. So that's why for this time or mini project, I don't have any presentation in the first few weeks. We only have it after the midterm. So next project is the computer simulation or advanced control strategy. You see, a motor control is quite an important topic for PhD or for master anyway. One of the simple control method is called VF control. I mentioned to you. We try to keep the ratio for V and F as a constant so that we're able to control the torques properly. Why VF is to be constant? Because in this case, the motor thrust, we can optimize the motor thrust into best performance. So that's why for simple control method, we use the program the V over F as a constant. So besides this control method, there's many other control methods. Of course, for this course, I don't require you to analyze a complicated method like vector control or torque control. That might be quite complicated. You just analyze constant VF control will be good enough. And then you see how you can use a meta environment or maybe develop your own program. If you like to use Python, you can therefore develop your own simulation platform to simulate a motor control system. But at least you need to simulate a constant VF control under various requirements. Then, of course, other things like the direct torque control, field on-net control, they're quite complicated. You can try them, or you can compare them with the simplified VF control. In many of the websites, you can also download the direct torque control or field on-net control as a comparison. If you like, there's many models available already in the web lab, so you can download them. So our criteria to see how you can able to produce dynamic torque response. That means when you change the load torque from 10 Newton to 20 Newton, how the speed can maintain constant. So that's the performance I look like, how to make the control become more robust. Because for motor, the winding resistance, the lead gauge are the component. These components are affecting the motor performance, the motor torque. So this parameter changes all the time. Change related to the current, related to the temperature. So we have to, this sentence you say, can we control the motor even though they're robust to their parameter change, like the temperature change, the motor is still robust. When the winding resistance change, the control is still robust. So that's what we like to do. You don't need to do all of that because we only it's only a mini project. Account for only 20 marks. So that's why you only do sufficient amount, maybe do a few analysis, which up to a report have 12 pages. That would be good enough. Okay. So the next mini project is called the thermal modeling analysis of electrical machine. We've been talking a lot in the electrical machine in the electrical manner, how we control them, how to control voltage, current, and the torque. But more importantly would be power losses. Motor is similar to a transformer, which also have winding losses, core losses. So this can account for, say, 5 to 10% depending on the motor performance. As I mentioned to you, a really large motor like EV or industrial drive, then the efficiency can be 95 down to 90, maybe 80 something. So you can see that there are 5 to 15% of the power losses. The motor need to distribute or try to dissipate properly, conduct somewhere. So in this case, the thermal model will be important. How are you going to model the thermal performance? Would there be any thermal model to deliver that? If you do a thermal model, how are you going to control the thermal model to help you to dissipate the heat, including some forced cooling? Would that be useful? Help us to reduce the heat. Once we reduce the heat, then the winding resistance will drop. The performance model become better. If you don't do that, when the temperature rise, the resistance of the winding will go up. The loss will also go up. Then the winding resistance go up further. That end up with disaster. So with a source cooling, very important. How we're going to do that? You need to make it together with the thermal model to see how the total structure look like. Mostly the computer simulation people only working on the electrical model. They'll seldom talk into the thermal model. But thermal model is important because you need to close the loop for the thermal model. In case the temperature rise, you need to close the loop for thermal in order to improve or increase the cooling in order to make the performance stable. So in here, your deliverable need to look into the thermal circuitry, thermal equation model, estimate parameter for the thermal resistance, even the thermal capacitance. You see that thermal resistance also thermal capacitance because all the thermal parameter, they do have capacitance. So not as simple as this. And then you need that relate to the machine geometry, the shape. For instance, some machine are too thin, you can help us to do the cooling. Some of them doesn't. So that's why that will be important. You need to try different kind of low cycle to see under a few low cycle, your design for your thermal model still valid. So that mainly computer model help us to design motor under certain constraint. Before when we design motor, we never think of the thermal, but now then you need to think about it, even though when you do some simple testing. So lastly, number 12 will be the literature survey for some novel machine technology. I think every day, every year, we got some new development for electrical machine. So in here, you need to do some literature survey to search for some latest development in the machine. What kind of new development? Would there be any axial flux machine? Would that be better? People are now talking about that. And the superconducting material, superconducting machine, and dual inverter feed system, open-ended winding, manual bearing, less magnetic bearing. So many of the new development. So you can choose a few or one important one to have the detailed analysis on that state of art of the machine technology, new technology. I like those technology brand new rather than, just a simple PWM inverter. So some new name. So, and then to see what kind of advantage, disadvantage of them, what's the costing they are, what's the future application, and also what's the challenge. So this, of course, is a pure desktop study. So in my requirement here, usually the desktop study I require at least about 12 pages. For hardware, 8 pages will be more than enough because you got hardware. You can also demonstrate your hardware. You can also video your hardware to show to us. So for desktop, we require slightly more number of pages to show you you've done a lot in your desktop analysis, right? But that's the only minimum, 12 pages. Something like usually in the past, the student may be 15 pages will be quite long, but 12 pages is my minimum. So the font size 12, synchronized spacing anyway. So, but for all the mini project, we need to select a time to present after the week of the midterm. Then we can start to present in the class about 15 minutes. If you do present a hardware, you can bring your hardware along to show the hardware working. And then you need to submit your report before the end of the semester, which roughly about the first week of December. And after that, that will be the exam. Then for the hardware, then you can come to my lab and BSP lab 30. Then you can go there. I think I all give you the access code. You can able to go there. If not, then you can contact me. Then the lab still empty at the moment. You can go there as early as possible to occupy good location there because the bench is there. I mean, a good location which you like, the best corner, best area occupy. If you put your stuff there, so put your name there. Oh, that's my working desk, something like that. Then okay. Then if you need some scope or any other equipment, I can also arrange that to set up your bench there to start your own work. You can first try it with this kind of the mini project if you like to do hardware. Any question up to this point?
So when should we design the project?
I will going to prepare a shared file. Then you can, in the file, you can write down which project you like to do, and then which time slot you like to present. I only allow one presentation per week after the midterm. So I think decision you can make after 2 weeks. Even though after you have made the decision, you want to change, also welcome. The thing is, I like you to write down your title first, so that push you to make the decision, start to do your research. But if you later on you change the new topic, that is your disadvantage, not me. So that's why I push you to give me the title within 2 weeks. Then you start to do your work. Okay. And then because for instance, you do hardware, you need to buy component, DC motor, something. All the components are not expensive anyway. But if you need any support from me, of course, I can buy for you. Then you can therefore start to do some hardware testing. If you need any support like equipment, oscilloscope, then we can also arrange that. At least for each student, they need to have a good set of hardware, oscilloscope, power source, signal generator, electronic load, this basic thing they need to have anyway on the bench. Then you can test anything as you like. Do prepare for it anyway. Any question? So this gives you some of the basic requirement. You see, for senior student like all of you, I don't like you to just go to the lab to do some mechanical type of the lab. You see, when you go to lab section, they just give you a lab sheet, ask you to follow the step one by one, really tedious, without any thinking. When you sometimes after you finish lab, you don't know what the lab is doing because you're not doing the lab, you're doing the step. I don't like that. So for senior students like all of you, you need to do project like this. That will be something you can explore, you can develop into any manner. You see, this project only give you a title and some small description, deliverable, but you can always vary your deliverable to something you can explore further. For instance, I only mention a few machines here, but you find another machine is wonderful, you can discuss it. And then, for instance, MATLAB model control, you can develop any control method. You think one of the control is marvelous, better than the one I mentioned here, you can do it. So it all depends on you. So we don't have fixed answer. You can change the deliverable as long as you can fit the title. So this kind of project very flexible, mainly to stimulate your idea of R&D, rather than fix you to follow the step only, which conventional undergraduate lab will do that, but not for postgrad. All right, any question? If not, then we continue with our teaching, all right? Okay, we stop here. I just should go to another file. So this chapter, we are trying to examine about transformer. So transformer is one of the really basic machine we need to study before we learn any motor. Why is that they're all similar? Transformer is the stationary machine, no moving part. A motor have moving part and also stator part. So that's the model of between them are really similar. So that's why for all the courses in electrical machine, we first need to study the transformer. So here we try to understand more about transformer and basic magnetic circuitry. Anyone have learned about transformer in your physics or maybe in your year 1, 2, 3? You have learned that. How much you have learned transformer? Tell me.
Yeah, like we will use a transformer to step up voltage and step down this purpose.
Okay, of course. And what else? How about the parameter, like the leakage component, magnetizing component? Have you learned them?
Yeah, about all the
Open circuit test?
about the liquid used in the transformer, how we can preserve from heating
Right. Okay.
and the leakage current and everything.
Good. So this chapter actually appears in most of the textbook. I think if you have gone through the undergraduate electrical engineering, you must have learned the transformer. Probably you have learned the transformer. Tell me your experience for transformer.
So I think I just learned something basic about transformer because we always will focus on the power electronics, for example, the bar boost. And I think it's not a very serious course to very focus on transformer. So for me, maybe in my brain is like the set up voltage and go down voltage and something like the middle of some material, for example, iron, enhance the focus transformer like that.
Okay. How about you? Tell me about your experience for transformer. Okay. But anyway, I started transformer from very basic. Some of them maybe you have learned it in the past. Some of them may be slightly good revision. Anyway, so what the configuration of transformer? I think we all know that. Two winding,
Yes.
primary side, secondary side, try to couple to each other through a magnetic core, right? It's a basic transformer. Then the major component for transformer must be two winding magnetic core. You see some transformer can be air core, so that means no magnetic core. So that can be also a transformer. Some transformer only a single winding. Like, let me see, some transformer, we call it so that's the input, right? Transformer will be like this. Have a tapping here, but this can be varied. Then that's output. So this transformer, we also call it auto transformer. If you go to the website, I don't know why you call this name auto transformer. So that means this one doesn't have any isolation between primary and secondary side. They share the same winding. To try to make transformer simple, but also able to change the voltage. Transformer usually have high efficiency, 90 something, 99, 98. But if you want to, really good for change voltage. So you can see that if a single winding inductor like this, we're tapping, we're able to adjust the ratio between input output like a transformer. So this is also called auto transformer. some of the long isolated transformer, if you want to change the voltage, like you have 200 volt three phase, you want to convert them to 120 volt, you use auto transformer to do that. So that's a simple way to do that. So that's why a major component of transformer can be two winding, can be one winding with a magnetic core, many shape. And then more importantly, for a transformer, we have many components like the transformer turns ratio, like the winding resistance, leakage component, magnetizing component. How are we going to measure that? So in this course, we're going to show you something, how we're going to measure the component. So in the lab, if we do have lab, then we can also do some measurement. So if you're doing any mini project, like your modeling, then you can also try to provide some kind of understanding from here. So obviously, the basic equation transformer will be voltage ratio equal to turns ratio. We all know about that. And then, do you think they're all the same? Would there be any condition they are not the same? For instance, when a transformer being loaded under heavy load, light load, of course, the turns ratio could not be always the same, equal to the voltage ratio. It won't be. It's so-called loading effect. Some power have been dropped in the internal resistance or winding, so we don't have such output voltage. So, and then in here, we need to understand more about it. So the basic ideal line condition will be voltage ratio equal to turns ratio. But we can use that opportunity to understand more about what it is. Okay. So this chapter, we're going through some introduction for the transformer history, and then we talk about some gap the inductor. The reason I can say gap the inductor because same as the one we mentioned last week, will be because the transformer gap is trying to reduce the magnetic flux. When we somehow have too high magnetic flux, we'll end up with some saturation. The transformer or maybe inductor may not be working really well. So that's why we need to make use of the gapped inductor in order to produce some air gap there. I think that is really commonly available in many of the power electronic development. In many power electronic inductor or maybe transformer, we put a small air gap. The air gap can be only 1 mm, maybe 0.5 mm, just like thickness or paper. A paper usually about 0.1 mm. Many of our engineers put a small paper between air gap in order to develop this kind of phenomenon. So later on, we'll talk about a bit more about the gapped inductor. And then we try to talk about inductance, how to calculate inductance, what's the formulation about that. And we have a sinusoidal excitation. How are we going to calculate this phenomenon, the magnetic flux in the transformer, to do that? And then ideal line transformer. How does the ideal transformer look like? And then we're also looking into practical transformer. Of course, then we make the conclusion. So here will be some history of transformer. We did talk about the history of the electricity or motor in the past, but transformer only a subset. I think in 1831, Faraday developed the principle of electromagnetic induction, which is a really good concept for the important step for all the transformer or generator and motor. So since then, he developed the electromagnetic principle, define the T or the voltage. That's the important equation. From there, then we can use that principle to develop a transformer. But of course, in theory, we try to say Faraday developed the define dt time number of turns equal to voltage, right? But of course, the other engineer, they just found that when they apply the AC or changing voltage, you can able to have some magnetic induction become magnetic flux. That magnetic flux can also induce voltage. At that time, they still examine about the Faraday's law, the magnetic induction, to see how accurate they are. They know the induction. They actually, when they develop this transformer, they don't need to use the Faraday's law. They just putting two winding there into a same magnetic core and found that primary, secondary side have the induction. They think that must be magnetic induction. During that time, they don't know how to measure magnetic flux. They have no sensor. But they feel that there's some kind of the attraction due to magnetization. And then from 1881 to 1884, they developed the AC transformer. During that time, they do have a generator to develop AC power, and then inject the AC into a winding like this one. They can therefore develop the transformer. So this picture shows us one of the famous prototype of the first transformer from Stanley, 18. I think I have typo here. That should be 18, right? In 1885, William Stanley developed his first commercial transformer, which already is in the museum to show the people how the thing being developed. And then since then, we also other development in 1885 simultaneously, Sebaslowski, he also developed his own closed core transformer. That means the magnetic core is closed. Before the magnetic core may be just like solenoid, not closed. Closed, and then performance will much better. Since they can close the magnetic core, so they can therefore have a much higher magnetization. So this become more commercialization in across the Europe. And then in 1889, he then developed different kind of transformer, the three-phase transformer. Because when we started to talk about high power, then three-phase will be important. So we started to develop how we change the single phase into three-phase transformer. So that's how the phenomenon look like for the history of development. So that means in the 19th century, the transformer has already well developed at near the end. So that's why that's important development for power distribution system. Another important area will be high frequency transformer. You see, today, most of transformer electronic system, we tend to work at 60 Hertz. 60 Hertz is the frequency we use for 110, 120, like the US, Canada, or Japan. In other countries, like in the Europe, UK, United Kingdom, or China, they tend to use double the voltage, about 220. And then the frequency will be 50 Hertz. So 50, 60 Hertz is considered a low frequency for all the power distribution or power generation. Why is that? Because for generator point of view, we try to make a dynamo or generator to rotate from the coal fire or from the hydropower. The common rotation speed would be something like a few thousand RPM, 3,000 RPM, 3,000 RPM. That frequency will be equivalent to the 50 to 60 Hertz. If you want to have rotation machine generator, 10,000 will be too high, unless they use some gearbox. So that's why commonly the power distribution will be 50 and 60 Hertz. And then when we talk about power electronic, the frequency can be much higher. Talking about kilohertz, tens or hundreds of kilohertz for the rotational speed. So that means for transformer, in power electronic, we tend to use much higher frequency. Mega transformer, kilohertz transformer is quite common. So the basic equation between two of them are the same, even though all the matrix equation parameters are the same. So we can study them together, but we do take a look to see high frequency, low frequency, what are the difference. So for the magnetic core, because of the development of fluoride material able to produce really high permeability. You see, most of the conventional transformer, we use silicon iron. Those iron E-shape form, put them together, become our transformer core. So this kind of the so-called silicon iron, their permeability are a few thousand, 3,000, 4,000, quite common. So that's a good material for the transformer. If too low permeability, we can't do any transformer. And then for fluoride, then we tend to work at high frequency. So the thing is, if you put the silicon iron at 60 Hertz, it's working really well. If we inject the frequency to 1 kilohertz, tell me what happened. Air core transformer, put 1 kilohertz, what happened? What do you mean? Go on.
Yeah, not sustain direct.
You become burned,
Yeah.
on fire,
Yeah.
or what? Firstly, the transformer will get very hot. Secondly, the magnetization, the mu-R, will drop down to really small, from 3,000, probably drop to 3. Why is that? Because for the silicon ion, the internal dipole is really big size. Under high frequency, they cannot follow with high frequency to rotate. So the magnetization will drop. The permeability of all the silicon ion may therefore drop down to really small permeability because it cannot catch up with the frequencies. The internal dipole cannot move so quickly. So secondly, there were high eddy current losses. Internally, there's a lot of circulating current in the silicon ion. They make the losses seriously. So that means firstly, getting red hot. Secondly, because of low permeability, internal resistance, internal leakage become really disappear. So just like a full current, full voltage go through the winding. And having said that, even though you try to control the current, but the magnetization is still really low, the permeability really low, you cannot induce any proper magnetic flux. So you cannot, the voltage conversion ratio to term ratio doesn't work. So that means we cannot using silicon ion for transformer for high frequency. We need to use ferrite. Ferrite is a material which is able to provide high frequency. They use the nickel manganese, really small powder. The size roughly goes down to micron size, and mix them with some kind of the filler. And then they press them to really high pressure, a few tons, to construct the core. Why they do that? Once they mix with the filler, then they can isolate the eddy current. Eddy current can flow because all the magnetic dipole are surrounded by the insulator. The eddy current cannot flow inside. You can therefore stop the losses. And then once, because the dipole is so small, they can therefore rotate with the magnetic flux in synchronous manner. So that's why you can able to produce high permeability. So that means for high frequency, we need to grant all the magnetic material to be really, really small size. Like megahertz, the material must be down to micron size. If high frequency, we may need to go down further. So this kind of ferrite more look like ceramic because it drop quite easily. We drop on the ground, we break. So very much look like kind of ceramic. But because they got high resistance to the eddy current, then therefore we can minimize all the eddy current loss, proximity effect, which laminated iron cannot do. Conventional 68 Hz transformer, we use lamination. That all the E core, they are all isolate each other. So that's how the difference is there. And high frequency transformer, we usually driven them by using power electronic circuitry, like the SMP switch mode power supply. Because during that time in 1980, we do have really good development of power MOSFET. We're able to drive all the DC converter, inverter, using high frequencies, tens of kilohertz, hundreds of kilohertz. So that's why we're able to develop high frequency AC, which is able to drive all the transformer. I think the key reason why we want to use high frequency transformer because of the power equal to E times F, right? The formulation. Let's repeat to you our important formula. That's my pen. Anyway. So key advantage of high frequency transformer will be mainly the oversize will be smaller because we use high frequencies. And the half Li square, the energy equal to half Li square. That's a famous equation we have. And then when we talk about power, we equal to time the frequency. Yeah. For the same power, then we can increase the frequency, we can reduce the inductance. So that's why we can able to provide much smaller size for the transformer once we work at high frequencies. And then when we use ferrite, we can able to reduce the power losses because we can already reduce all the magnetic losses, eddy current, proximity effect. So because we use ferrite, then that's why the high frequency losses of the transformed magnetic material become much lower. So the application for this high frequency transformer, including power supply, many of the power supply today, like the charger we have, there's a number of chargers in the system. Then you can see that the charger much smaller than 10 years ago or 20 years ago because we use high frequency transformer inside. And even though all the design we need to match up with the radio frequency and also impedance matching. And for the renewable energy, then even though we develop the inverter or solar power distribution, we also need to make use of the high frequency transformer to transform the voltage from one stage to another stage. Each vehicle, we need to convert the AC group into DC. Between them, we have transformer for the isolation and also support with the charging system. So the basic reasoning why we have to use the high frequency transformer. Second section will be the gated inductor. And a transformer core like this, or inductor core like this, with a basic winding. And then we usually may need to include air gap. The air gap here is to produce us with location. Firstly, you can store some magnetic energy. Secondly, we want to reduce the magnetic core resistance. The thing is, if we have no air gap, all these are silicon iron or ferrite, the metallization is high, the resistance or so-called the reluctance will be much lower. Once you energize with MMF, maximum motive force, or so-called the input, then we can produce high magnetic flux. If the flux is too large, it may saturate the inductor. So that's something we don't quite like. So by introducing air gap in an appropriate manner, we can control or introduce another term of the resistance so that we can able to reduce the magnetic flux. Here will be the equivalent circuitry. The driving force called the MMF, the symbol called F, will be equal to N times I, current times the turn ratio. So in this case, if we want to increase the driving force, we can increase the number of turns. Very straightforward. But the magnetic core will have its own reluctance, which is produced by RC here, reluctance. You see the R symbol, we use a special double form here, represent the reluctance, so that you can differentiate it from the resistor R. And then we also have air gap resistance due to this air gap. So the basic principle for the reluctance is this one. I think I introduced to you last week. So that would proportional to the length of the flux traveling divided by the area, cross-sectional area in here, and also divided by the permeability. You see for the magnetic core here, the permeability usually quite large, like the relative permeability will be a few thousand. So here will be quite, so RC, you can see that will be quite small once the mu C is really large. But for RG, we don't have any relative permeability here, it's only equal to 1. So that's why in here, this will be equal to mu log. So for the mu C here, I think you all know that the mu C equal to mu log mu R. So this one is 4 pi and 10 to the minus 7. Mu R is for ferrite, for powder iron, will be a few thousand, maybe 3,000 to 4,000 or whatever, around this kind of parameters. So that's why I can see that once we have this term, a few thousand of mu C will make this the whole reluctance to be quite small. But in here, because only mu log without for air, this term will therefore become equal to 0 for air. So that means the mu C will convert into mu log anyway. So that means RG can be quite large. So this large item can therefore reduce the magnetic flux passed through the winding. So total flux will therefore equal to the input divided by two reluctant here. I shouldn't have the pi here. Ignore the pi. So the core flux density, we call it B. So that the form more concern to us, because for all the magnetic material, they care more about the magnetic flux density. So that means this flux divided by area with the B field. So in theory, this flux, the phi, will pass through the magnetic core plus the magnetic core material. Of course, there may be fringe field in here. Fringe field? Fringe field means field pass through in here. Sometimes some field will pass through in here, but some fringe field. Fringe field will adjacent. So that make the air gap area look bigger. But if the air gap is small, then probably the fringe field will also less. So, but in many cases, we can assume AC equal AG anyway, because if the air gap is so small, these two areas are really much the same. The fringe cannot go to too far away anyway. So in this case, you can assume the B field will be these two, but of course, these two will be equal anyway, because the flux C and flux G will be the same, because the flux are passed through the same path. So that's it about the gap inductor. We'll continue next week. Oh, no, Thursday. Then we can continue with the rest of the section. Okay, any question up to here? Okay, then see you again Thursday then.